Today, we're going to continue looking at area under a curve and talk about why we only need to worry about area is equal to length times width. Whatever the shape is, we're going to go with area is equal to length times width. When we have a constant length, then we get to multiply constants, and that's our favorite. That's the original area that we learned. Area is equal to length times width. This works as long as the length is the same for the entire width. If we have a shape where the length is variable, so I have the width in the same place, but notice that the height or the length is determined by some function. Our strategy is to break this down into lots of instances of the previous case. We assume the length is constant for small changes in the width and make rectangles. This way we get to use the constant length idea. We get to multiply constants. So once we assume length is constant and make rectangles, now we get to multiply, then we have to add up the areas of the rectangles. So now we get to multiply. So now we get to multiply, but we have a bunch of areas of rectangles. So then we have to add up the areas of the rectangles. So once we have this low res version of the shape or the area that we're looking for, we get to use multiplication. Then we just have to add up the areas of all the rectangles. We know that if we use more rectangles, the little pieces that we're including or not including, the little bits of error will become smaller. More rectangles means less error. See, here we have some overestimate. Here we have some underestimate. We know that more areas gives us a more accurate approximation of the area. We know that more rectangles means a more accurate approximation of the area. And so calculus just says use an infinite number of rectangles. So the calculus solution, if doing something more often makes your approximation better, then do that thing infinitely often. We did this when we wanted to when we approximated the slope of the tangent line with the slope of the secant line. The closer we put those 2 points together for the secant line, the better our approximation of the slope was. So we made those 2 points infinitely close together. The same thing is going to happen here. We'll have the more rectangles that we use will give us a better approximation of the area. So the calculus way is to use an infinite number of rectangles. Doing a thing more often improves your approximation. So do that thing infinitely often. This is the calculus way. So let's take a look at an example where we're kind of forced to do this. And I'm going to look at, oh good, it's always increasing. So an example of where we're forced to do this is when we want to calculate an area, well, we're going to use distance is equal to rate times time. So instead of area, we'll use distance, and instead of length, we'll use rate, and instead of width, we'll use time. And what we have is a set of data where we have time measured in seconds and rate measured in feet per second, because old school. So what we have is at time t equals 0, we have a rate of 20 feet per second. Then at time t equals 2, the rate has increased to 30 feet per second. And then at 4 seconds, our rates increased to 38. Then at 6 seconds, the rates increased to 44. 8 seconds, we're up to 48. And at 10 seconds, we're up to 50. So what we're going to do is, so we notice that the rate increases from 20 to 30 from 0 to 2 seconds. So one thing that we can do is just say, well, let's get a lower bound on the distance by just using 20 as the rate for that whole first 2 seconds. So in this first 2 seconds, we're going to make the following assumption. When we have variable length, our rate is variable. We assume that the length is constant and make rectangles. So the thinking can be, let's just suppose that the car, what is this, a car? Yes, it's a car. That the rate was 20 feet per second for that whole 2 seconds. So that the distance in that first 2 seconds is rate 20 times time 2, or 40 feet. So this is going to give us a lower estimate. We can also get an upper bound by using the 30. We could say that for the first 2 seconds, the rate was 30 feet per second for 2 seconds. And so we can use the 30 for an upper bound. So we could also say that the rate was a constant 30 feet per second for 2 seconds. So that distance will be 30 times 2, or 60 feet. And we'll say that the distance for that first 2 seconds is somewhere between 40 and 60 feet. Now, if something weird happens in the data, like at 1 second, it was at 100 feet per second, and then it dropped back down to 30, all sneaky like, and I don't tell you that, I'm just cheating. So we just have to take the data that we have. We don't get to speculate as to what might have happened, because that's called making stuff up. Sounds funny when you just talk about making stuff up, but one of the reasons that we're still in the midst of this pandemic, one of the contributing factors is people making stuff up. So Measles is making a comeback because people make stuff up. So it's a little bit more serious. But that would be cheating on my part to just say, oh, but I didn't tell you that it went up and then back down to 30. That would be just cheating. So that was the big idea. Our rate is increasing from 0 to 2, between 0 and 2 seconds, from 20 feet per second to 30 feet per second. We just make it flat. That way we can calculate distance as rate times time. Now I just need to do this for a bunch of rectangles for each 2-second interval. So let's take a look at this data again. Same example. Distance is equal to rate times time. And we have time in seconds and rate in foots per second. At 0, we have 20, 2, 30, 4, 38, 6, 44, 8, 48, and 10, 50. So a lot of times what we'll do is say if it's between 40 and 60, then we'll just average those two and call them 50. That makes an assumption that it was linear between 20 and 30. Every time you take an average, you're making a linear function. Notice that going from 20 to 30 to 38 to 44 to 48 to 50 is not linear, but it's quadratic. So it's a plus 10, plus 8, plus 6, plus 4, plus 2. So the rate of change is not constant, but the rate of change of the rate of change is a constant -2. So we're dealing with a parabola. So let's approximate the distance using a lower bound. On each of the 2-second intervals, we'll use the lower of the rates. So approximate the distance let's see. Find a lower bound for the distance. Let's find a lower bound for the distance from t equals 0 to t equals 10. What we're going to do is use the lower of the two numbers on each 2-second interval. Once again, the idea is that we make it flat so that we can use multiplication. So in the first 2 seconds, the lower is 20 feet per second, and I'll multiply that by the time 2. Then on the second interval, I have 30 and 38 between 2 and 4, so I'll use the lower one, 30. On the third interval, I have 38 and 44, so I'll use 38. On the fourth interval, I'll use between 44 and 48, I'll use the lower one for 44. On the next interval, I'll use 48. And this is how we'll approximate the distance in feet. And this will provide us a lower bound for the distance traveled because I used the lower rate to represent the entire interval. So if we add all these up, we get a lower bound of 360 feet. The distance traveled is at least 360 feet. We could do the same thing. We could find an upper bound for the distance. And in this case, instead of using the lower rate on each 2-second interval, we'll use the higher rate on each 2-second interval. So on the first 2-second interval, from it's between 20 and 30, we're going to use the value 30. On the second interval, we'll use the 38 because that's the higher one. On the third interval, we'll use 44. On the next interval, we'll use 48. And on the last interval, we'll use 50. So we calculate this, and we get 420 feet. The actual distance traveled must be somewhere between 360 and 420 feet. 360 because we were using the lowest value of the rate on each 2-second interval, and 420 because we were using the highest value, the highest rate on each 2-second interval. This is still from t equals 0 to t equals 10. So what we're saying is that the distance is somewhere between 360 and 420 feet. If we wanted to improve this approximation, we would have to know the rate more often. We would have to know the rate at smaller intervals. So notice that the difference between the two is 420 minus 60. So that's a difference of 60 feet. So we're plus or minus 60 feet here. And that's not very good when we're talking about 420 feet. If you're talking about finding a place, a spot on the moon, plus or minus 60 feet, probably pretty good. Because that's a long way away. But on the order of 360, you don't want to be off by 60. So if we had the rate if we had more data, if we had the rate at smaller intervals, then we would be then that would bring the lower and upper bounds closer together. More rectangles makes things more accurate. More rectangles improves the accuracy. Any questions? This particular problem used distance is equal to rate times time. That's just standing in for area is equal to length times width. It's just that the length was feet per second and the width was in seconds. So our area was in feet. So this would be the same as if we had area is equal to length times width, and I had the length in feet and the width in feet. My area would be in square feet. And it would be 360 square feet and 420 square feet. If instead of calculating distance or area, I was calculating work as force times distance, and my distance was in feet and my force was in pounds, then I would still get 360 and 420. It would just be 360 pounds feet and 420 pounds feet. Any questions? So if we think about what this looks like, do I have space? A lot of extra t-axis. There we go. So if we look at this on a graph, let's have time down here in seconds. And here's going to be our rate in the vertical in feet per second. At 0 seconds, we'll be at 20. At 2 seconds, we'll be at 30. At, let's see, 2. At 10 seconds, we're going to be all the way up at 50. At 4 seconds, we're at 38. So not right there. At 6 seconds, we're at 44. 20, 30, 40, 50, 45, a little bit less. And then at 8 seconds, we'll be at 48. So here is what our graph might look like if I draw a smooth graph between connecting all these points. Our lower bound said instead of increasing from 20 to 30, our lower bound drew this rectangle for the first 2 seconds. For the next 2 seconds, we used the 30. For this time from 4 to 6, we use the 38. From 6 to 8, we use the 44. And from 8 to 10, we used 48. So here's graphically the 5 rectangles that we used to calculate our area of 360 feet. Remember, our area is 360 feet because the vertical is measured in feet per second and the horizontal is being measured in seconds. Any questions? So if we look at all these little gaps, this almost triangular area above that first rectangle, that's how much underestimate we have. There's area that we're not capturing by assuming that the first 2 seconds is a constant 20 feet per second. But if I have data at, say, 1 second, if I'm able to use, if I have data more often, then even underestimating, I'm going to grab chunks of area that we weren't measuring before. So if we had data at 1, we could see we could get rid of some of this missing area. If we had data at 3, the same thing. We would get more of this missing area. More rectangles improves accuracy. Any questions? How's everybody okay?
Professor Leach, I have a question. Is it related to the secant line and the tangent line earlier you mentioned? Are they related? If we
Not quite. We're not in the tangent line question. I would be looking at the curve, and I would be picking 2 points and finding the slope between those 2 points and then bringing them closer together. Here, we're doing a different calculation. We're trying to calculate the area under a curve. So we're trying to do length times width, but our length is all variable. So I can't just multiply. Our length keeps changing. So we're doing a different problem.
Got it. Okay. Thanks, Professor. I see it.
There is similarity because as we in the tangent line question, when we bring those points closer together, our approximation of the slope improves. So the calculus way is to bring those points infinitely close together. The same thing is going on here in that more rectangles means a better approximation. So the calculus way is to use an infinite number of rectangles. Here with a change in t of 2 seconds, if we reduce the size of each width, then our approximation improves. So we'll want to make these rectangles infinitely thin, and then that would require an infinite number of rectangles. So that's all the thinking that goes around finding the area under a curve. We want to use length times width because we want to multiply constants, but the length is all variable, messes everything up. So we assume that the length is constant for small changes in the width so that we get to multiply constants. Now we want to move on to phase 2 of the thinking behind area under the curve. Here's another way we could think of what we're doing. This is another big picture thing that we're thinking about. We're adding up values of the function. We're just adding up values of the function. So let's suppose that we have some funky function. Let's suppose we want to find the area under the curve f of x and above the interval, let's say from A to B. We want to find the area under the curve. Usually we just say under the curve, but we want to find the area under the graph of the function and above the interval from A to B. So find the area under the curve and above the interval. Excuse me. Suppose we want to find the area under the curve and above the interval from A to B. This is our classic problem. We want to use length times width, but the length is all variable. The length is given by the value of this function. Not only is the length changing, but unlike the previous problem where the length was changing every 2 seconds, here the length is changing continuously. So we're going to do the rectangle thing. We're going to break the interval from A to B up into subintervals. And on each subinterval, I'm going to assume that the function is constant. So we're going to divide the interval AB into a bunch of subintervals with the width that we'll call delta x. So divide the interval from A to B into subintervals with width delta x. Capital delta x is our delta is the letter that we use to represent change. So, and the capital delta, so that triangle. So we're going to divide the interval AB into subintervals, each with a width of delta x. So each of these widths is delta x, and in this case we can see we have 4 subintervals. Now what we're going to do is we need to pick a value for the function by picking some value for the function on that interval. So on each subinterval, we're going to choose an x value, and we're going to evaluate the function at each of those points. So now we'll choose an x in a value of x in each of the subintervals and evaluate the function at that point. We're going to choose a value of x from each subinterval. And evaluate the function at each of those values of x. So I'm going to say x1, x2, x3, and x4. They just need to be some value of x from the subinterval. In the previous problem, all we could use was the left endpoint or the right endpoint because that's all we had. Here, we can pick what we want. Now, we're going to evaluate the function at each of these values of x, and that's where we're going to get the height of each of these rectangles. That's how we're going to flatten out this curve. So the function, so here we chose x1, x2, x3, and x4. So the function at each of those subintervals is going to be the height of the rectangles that we create. So the heights of each of these rectangles are f at x1, f at x2, and f at x4. And we're going to flatten out each of these, the function at these different heights. Now we're going to calculate the areas. So the area is f at x1 times delta x. That's that first rectangle. Then we have the next rectangle, f at x2 times delta x. The next rectangle is f at x3 times delta x. And the fourth rectangle is f at x4 delta x. It looked different when we made this calculation before because I had numbers 20, 30, 38, 44, 48, and 50. Notice that each of these rectangles, each of these areas has a common factor of delta x. So in that sense, that's why I'm saying we could think of adding up the values of the function. Since we used the same width for all the subintervals. So one way we can calculate this area, since we're just evaluating the add up all the heights and multiply by the common width. So here, all we did was factor out the width. Now, we know that using more rectangles will improve our approximation, and that using an infinite number of rectangles should give us the exact value of the area. So to look at that some more, we need to introduce a kind of notation called summation notation. So we have our area. Which are these four rectangles. Each of the terms has the same form. So we want to notice that each term has the same form. The form of each term is f at x sub something times a delta x. All four terms have the same form, f at x sub something times delta x. So what we can do is, since all the terms look the same, the only thing that's changing is the index x1, x2, x3, x4. Let's write down the same form with a generic index I. Where I is the index. That's bad grammar. I am the index. And we'll just say, of the things like this, add them up. So we use a capital sigma, and then we tell what values of the index to use. I starts off at 1 and ends at 4. So this is how sigma notation works. The sigma means find the sum as I goes from 1 to 4 of f at xi times delta x. This is the sum as I goes from 1 to 4 of f at xi times delta x. That means you plug in 1 for the, then 2, then 3, and then 4. This sigma notation always counts by integer. The reason that we want to do this is that this is the expression for 4 rectangles. What if we wanted the expression for 10 rectangles? I don't want to write 10 terms because they all look the same. I could just write the sum as I goes from 1 to 10 of f at xi times delta x. Or if I have 100 rectangles, I can write the sum as I goes from 1 to 100 of f at xi times delta x. So that's what we're going to look at next. What do we do today? We reviewed the concept, area is length times width. We get to use multiplication of constants if the length is constant. If the length is variable, then we have to break the area into a bunch of rectangles, so we can just use length times width. We talked about sigma notation and how we'll find the area under the curve by using the value of the function at a bunch of different points. And that's how we flatten out the function. And then we talked about this sigma notation business, how we summarize our results or what we're going to be calculating. All right, so that's going to do it for today. Tomorrow we'll look at some more examples of sigma notation and how we can interpret that as an area under a curve or an approximation to the area under a curve. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.
Thank you.